Right. So we are talking about the when the ground state. I'm talking about the transition between the non-degenerate systems. Okay, in the orbital selection rules, and in that we are talking about the when the ground state is not totally symmetric. Okay? In that, I told you that if you take an example, the transition when it is happening like this to be allowed, okay, what is the criteria? The irreducible representation of psi of the orbital in the ground state, multiplied by the psi function of the orbital in the excited state should be equivalent to the what is mu I? Mu I is nothing but your electric dipole moment. Okay. So we are telling that it is not totally symmetric ground state. So I will take it as A2. I told you one thing that if we are talking about the totally symmetric, the symbol will be A1, A1 prime or A prime. Okay. When I am writing A2, it means it is not totally symmetric. This is given by the Mulliken symbols. Okay. So which you will be studying in the group theory chapter. Okay. So when I am telling this is equivalent to A2, I am just putting this value here, the reducible representation. Then this and this as it is we have written. Okay. So when you see this in the CTV point group, what happens is I said A2 is a ground state. Then the excited states can be B1, B2 or A1. Then that will be equivalent to the irreducible representation of mu I. I said how to get this. Okay, so from A2 to B2. Okay, what is the polarization and how is that you are getting mu I in between? I just have a table here. Just see this table. Okay. Can you see this table? So what is that I have written here? I have taken the C2V point group only. Okay. So these are the irreducible representations of the ground state, and these are the, that's why we have written irreducible representation psi function of the ground state, and this is for the excited state. Okay. Now these are for the ground state and these are for the excited state. Okay. Now from the character table, C2V character table, we very well know that A1 means Z, B1 means X, B2 means Y. Okay. Then we don't have any notation for A2, so we have written 0. So same thing I have written A1 is Z, A2 is 0, B1 is X, same thing here, and B2 is Y. Please follow, I am doing it very slowly. So what is that I have written? I have written the irreducible representations in the ground state, okay, here, and in a horizontal manner I have written the again the irreducible representations in the excited state. Okay, and from the C2V point group we know that A1 is nothing but Z, corresponds to Z axis, B1 X, B2 Y, same thing here, A2 is 0. Okay, then what is that we are writing? Wherever the, if it is A1 into A1 cross link, it is Z. Okay, so A2 into A2 it is Z, B1 into B1 it is Z, B2 into B2 it is Z. Okay, wherever it is cross multiplied or direct product of the same, okay, then it is in the polarized in the Z axis. Okay, now coming to A1 and B1. Okay, we know that A1 and B1 is always X. Okay, so A1 into B1 is X, A1 into B2 is Y. Coming to the A2, okay, A2 into A2, I said it is Z. So first remember this we have written, this part we have written, vertical and horizontal. Then I have put the as it is these values. Okay, so A1 means Z, A2 means 0, B1 means X, B2 means Y. Here also A1 is Z, A2 is 0, B1 is X and B2 is Y. Now we are left with this part, how to write this. Okay, so what I can do, I know that whenever it is the same thing, I can put Z's. So I have written Z, 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 Z. Okay, now coming to the this part. Okay, so A2 into B1. We know that B1 is X. So whenever I do the cross product with B1, it becomes Y. And whenever I do a direct product with the B2, it becomes X. So I have Y and X. Now coming to the B1. B1, what is that I have written? Whenever it is B1 and A1, it is X. B1 and A2 is Y. B1 and B1 is Z. Okay. And B1 and B2 is 0. Similarly, here we just write the other way around because I am talking about B2. B2 and A2 will be X. So 2, 2. B2 and A1 will be Y. B2 and B1, here also it is 0. Here also it is 0. And B2 to B2 is again Z. Okay, so this is a simple thing. Okay, from this we can take, just remember what is that we have written here. A1 into, so if you take this transition, what transition is that I am talking about? A2 to B2. Okay, A2 to B2. A2 to B2. So what is that I am getting? A2 to B2, X. X means what? The mu should be B1. Okay, mu should be B1. So that is the reason we have written B1 here. Okay. Now take the second transition from, because we are telling A2 is the ground state. Next state if it is B1. Okay. If it is B1, A2 to B1, A2 to B1. Okay. What is the thing that is shown in the table? It is showing it is Y. Y means what? B2. So we write the mu I value, that is the electric dipole, is E2. Okay. Now look at A2 to A2. Okay. A2 to A2. A2 to A2. It is Z. Okay. It is nothing but Z. Z means what? A1. So we have written here the mu value as A2 into A1 into A2. So you have got this mu value from that particular table. So this is X polarized, this is Y polarized, and this is Z polarized. So this is how the transitions are taking place. So these are all allowed, and this is how you get from the C to B point group. Okay, so you should have the two tables. One is the C to B point group. Okay, the other one is this table where the direct product table of that particular point. Okay. Now, so these two are, this is what we have to study under the transition between the non-degenerate, okay, transitions between the non-degenerate states, okay, when the ground state is totally symmetric, and the second one is when the ground state is not totally symmetric. Okay. Then we will move on to the next part, that is when it is happening between the two different degenerate states. So till now I was talking about the same degenerate state. Best example is C2V point group. Okay. Then when we are talking about the different degenerate state, that is the multi-dimensional factors. Okay. We will be talking about D4H and the octahedral as the best examples. Okay. So for the first one, when it was non-degenerate, I said that the direct product should be equal to A. Okay. And for the second one, when I'm talking about the different degenerate states, okay, the direct product should contain A. Okay, that is a totally symmetric representation A. So when I do the direct product, okay, this part, then it should be complete, should contain the A. Okay, then only you tell that the transition can take place. Okay. Now same thing, if I put in the X, Y and Z directions, I can write all these things. So if I am talking about in X direction, Y direction or Z polarized direction, all these equations, they should, all these direct products of the irreducible representations should contain A. Okay, that means they should have one irreducible representation which is totally symmetric. Then only you can tell that that transition can take place. The direct product, whatever answer you are getting, you should have A as one of its unit. Okay. So we will just take the example, that is the, I said you can take two examples, that is D4H and octahedral point group. So here we are talking about the talking about the octahedral point group, that is, we know that from the octahedral, uh, I'll just show you in the Jamboard. Uh, yeah, just see this octahedral thing. So X, Y, and Z. So you can see it here. So just see here X, Y, and Z. I think it's too small. So this is a T1U where you can see this X, Y, and Z. Okay, so this X, Y, and Z is nothing but this X, Y, and Z. What is the symbol you are seeing? T1U. Okay, T1U contains all the three. So same thing we are showing here. What is that? That is the irreducible representations in the X, Y, and Z polarizations. It is contained in only one symbol, that is T1U in the octahedral point group. Okay. So when we take in the octahedron, okay, when we take the ground state, if you assume it to be A1G, okay, why am I telling it's A1G? Because we know that, hope you just take it as A1G. We are assuming that the ground state is A1G. Okay, whenever I am writing it is A1G, it will be totally symmetric and it will be a non-degenerate system. Okay, then the transition to occur, okay, from here to here, you have to take the direct product of these two that should contain this A1G, that is the totally symmetric one. Okay, so to satisfy this thing, what should happen? The value of the irreducible representation of the electric dipole should be equivalent to the psi function of the excited state. Psi function of the excited state. Okay. And we know that the mu of the irreducible representation of mu I is nothing but T1U from the point group. Okay. So when I put this T1U here, it becomes the irreducible representation of the psi function of the excited state is nothing but T1U. So you can expect that only one transition will be occurring in the octahedral point group because the direct product this into that is becoming T1U. So the transition is from A1G to T1U. A1G to T1U. Okay. So from this we can tell that whenever it is a non-degenerate point groups, okay, the transitions are allowed between a totally symmetric ground state and excited electronic state whose symmetry species is same as that of the dipole moment. That's what we are telling, that it is same. The excited state is same as that of the dipole moment. So you take it as this one. Okay. So that is what we have given in the form of a selection or the definition. Okay. Dipole moment operator. Both of them are same. Okay, same. Now, if we are talking about symmetry of the ground state, if it is changing, the excited state will also change so that it produces a direct product. So, if I was talking about A1G, you are getting the totally symmetric. If I am changing the ground state electronic level, even the excited state electronic level should change. Okay, and it should written as like this. So, in the if I am changing instead of writing A1G, if I am writing T1G, okay. So it octahedral can have all other transitions like T1G to A1U, T1G to U, T1G to T1U, and T1G to T2. So these are all the transitions it can have if I am changing the ground state. Okay. This A1U, EU, T1U, T2, you'll understand bit better when we do some correlation diagrams and all. Okay. So just remember that that here the transition was only one when I'm talking about the ground state as A1G, okay, to T1U. And if I take a different ground state, that is T1G, the transitions are becoming 4. So you can study this using a different method. So you have a different method where you can see how these transitions are taking place. You can predict, okay, some what are the allowed transitions, okay, whenever you are given a given point. How can you do that? You have to draw this table. Just now I have shown you this table, okay. So how to do this table? First you are putting the irreducible representations of the ground state vertically, okay. Then excited state horizontally, okay, irreducible representation. Then you fill the mu I functions, that is x, y, z, and 0 at the wherever it is A2, you don't have 0, you don't have any x and y, okay, as well as some points. So at the crossing points, you put the mu I functions as well as 0, okay. What does that 0 denote? Denotes that they don't correspond to any of these polarizations, that is x, y, and z, okay. So if you take this example, C2 point 2, so mu I ante in the x it is B1, mu I in the y it is B2, okay. And the direct product is that when I do the ground and excited state, it should be equivalent to the mu I. So the direct product should either equal to a totally symmetric or it should contain the irreducible representation which is totally symmetric. Okay, then only this is an allowed transition. That is what you have to understand. So when I do the direct product, either it should contain the totally symmetric irreducible representation or it should be equivalent to the totally symmetric irreducible representation. So if I do A2 into A1, this is not having, this is 0, that means this transition is not allowed transition. Okay. What is the other not allowed transition? Okay, B1 to B2. What is happening? It is not in the either x, y or z direction. So it is not containing the mu I. It is 0. So this is not a allowed transition. Again, B2 to B1 is not allowed. A1 to A2 is also not allowed. So wherever 0 is there, these transitions are not allowed. Whereas if it is x, y and z, those transitions are allowed. Same thing we have written here. So these are all the allowed transitions. So A2 to B1, which is non-zero, is a allowed transition. A2 to B1 is allowed. Okay. A2 to A2 is allowed. Okay. Whereas if it is a 0, that is A1 to A2 transition, you have a 0 at the crossing, so it is not a allowed transition. A2 to A2. A2 to sorry, A2 to A1 is not a allowed transition. Yeah, A1 and A2. A1 and A2. So this is not a allowed transition. Are you all following? Anybody please tell me? Hope you are all listening. Emma పిల్లలు అర్థమవుతుందా?
Yes, ma'am.
A table lo unnade I'm just showing. Okay, so from this table also you can tell which are allowed and which are not allowed. Okay, so that is what we are telling from this table. So this is one more method where we can predict, okay, whether the transitions are allowed or whether the transitions are forbidden. Okay, one thing you have to remember is it should be equivalent to the totally symmetric irreducible representation or it should be contains the totally symmetric irreducible representation. Okay, so you can write all these transitions which are allowed transitions: A1 to A1, A2 to A2, B1 to B1, A1 to B1, A2 to B1, B2 to B2. So how many? 1, 2, 3, 4, 5, 6, 7, 8. So just see in the table. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so all these are the allowed. Okay, what are the other not allowed things? Forbidden transitions, you have A1 to A2, B1 to B2, and so on. Wherever you get 0, those transitions are not allowed transitions. Okay, remember one thing, from B2 you cannot go down. Okay, B2 is a higher excited state. We have written here, right? B2 is coming down and the energy is increasing this way. Energy is also increasing this way. So I can write A1 to A1, A1 to A2, A1 to B1, B1 to A1 to B2. ఇక్కడ A2 నుంచి ఇవన్నీ. Okay, B1 నుంచి B2 కి రాదు. Only from B2 to B2. Okay, remember that. Okay. Now we'll see what are the consequences. What is that we have learned? Till now we have seen in the symmetry notations, that is using the reducible representations, we were telling whether the what should it contain, then only it is allowed. Either it should be equivalent or it should contain the totally symmetric one, then only it is the allowed transition. Otherwise, it is a forbidden transition. Okay. Now we'll tell how to tell. Okay, consequences of this selection. Okay. So we are identifying these ground and excited energy states in the form of the symmetry, whether it is a degenerate, non-degenerate, as well as parity. Okay, parity means whether it is gerade, ungerade, and all. Okay, so whenever it is eccentric means whenever it is not having any center of symmetry, that is the I symbol of symmetry element. Okay, it will not have any parity, that is it will not have any gerade or ungerade. We don't put them. Okay, it means that it is eccentric molecule. Okay, so there is no need to talk about parity. If it is eccentric, you can simply talk about the symmetry and the orbital degeneracy. Now, if I am talking about centrosymmetric, I should even talk about this parity, that is whether it is a gerade or ungerade. We write, right, in the octahedral crucible theory, you write that it is T2G and TG. So you write G there. G means that is a gerade. Okay. Whereas in the tetrahedron, we don't write any gerade G. We simply tell it is from E and T2. It is breaking into E and splitting into E and T2. Okay. So that means it is an eccentric molecule, tetrahedral molecules. Whereas the octahedral molecules are centrosymmetric molecules. They have the center of inversion, whereas this is not having the center of inversion. So if it is having center of inversion, symmetry element, you have to talk about the parity, whether the orbitals are gerade or ungerade. Okay, so to know what is the dipole moment, you should know this. Okay, so this gerade and ungerade, when I do the direct product, okay, so G into G always gives G gerade. So when I do the direct product of two ungerade, I will again get a gerade. And when I do a combination of the reverse way, that is U and G, we will get, yeah, here it is. U and G, we will get U. Okay, remember this one. So these three things you have to remember, that is G into G gives G. Okay, and U into U also. So whenever I am doing the same parity direct product, so G into G, U into U, I will always get a gerade one. Okay. If I am doing cross one, U and G, I will get a, so either I do this way or that way. Okay. So what is a G into U or U into G? I will end up in U, ungerade molecule. Okay. So these three you have to remember. And whatever the electric dipole moment we were talking the same thing, is nothing but the dipole moment operator when I'm talking about the parity. Okay. So what is that we write? So when I am doing this direct product, we said that from that equation, if you remember, we used to write mu I. Now this mu I is nothing but your U. Okay. So instead of writing mu I, we are putting simply U. U is nothing but a combination. It can be a combination of G into U, or it can be a combination reversal. So either I do a direct product of G and U or a U and G, both you are going to get the U value. Okay. So when I do this thing, okay, what should happen? If it is a allowed transition, I should get a the totally symmetric, that is the parity should be generated. That means it is totally symmetric. So if I do the direct product of the ground, okay, then the dipole moment and the excited state wave function. So I very well know that this is the ground is totally symmetric. Okay, then this dipole moment and this one, these two, I can either I can, this is again mu is u. Okay, now this excited state, it can be a unjarred one or it can be a jarred one. Okay, so we will just take the first case when it is unjarred. So this is mu e, ground is the ground state, mu is u, we have seen here. Okay, and we have written so u. So what happens if I do keeping this g here, mu into mu, I know that it is g, so g into g, again I will get g. Suppose if the ground state is unjarred one, and if I'm having a excited state a jarred one, so what happens again, mu into u, I have g, and g into g, again you get. So whatever, whichever combination you do, you are ending up in a, you should end up in a jarred one. Okay, so if only it is getting that the triple product, if you are getting is g, then only it is Laporte or parity or orbital allowed transition. Okay, otherwise it will be a forbidden transition. So you can state that this electron dipole transition between states of same parity, that means U to U, G to G, are forbidden. So what is that? Whenever you are having the center of symmetry, the parity you have to remember is if the transition is from the gerate to gerate or U to ungerate, it is a forbidden transition. Whereas when the parity is different, it is allowed. If you remember, I have shown you what is Laporte in the last class. That is delta L should be equivalent to plus or minus 1. Then only it will be allowed transition. If it is 0, then it is again forbidden, and if it is plus or minus 2 also, it is again a forbidden transition. So what I can tell, if delta L is 0, how can it be 0? If it is from s orbital to s orbital, p orbital to p orbital, d orbital to d orbital, f orbital to f orbital, all these are the L values are same, so difference will be 0, so it is a forbidden. Then next one, just take 2, that means if I am going from 0, d value is 2, right? When I'm taking the L values of S and D here, S is 0, D is 2. So the difference between these two is 2. So again, if I'm going, if it is 2, it is a forbidden. So S to D is forbidden. P to F is also forbidden because the L value of P is 1 and the F value of, so L value of F is 3. So the difference between 3 minus 1 is 2. Again, the delta L is 2. So the value, the transition is forbidden. But if you take this one, that is when I am telling that it is only plus or minus 1. Okay. What is happening is S is 0, P is 1. So the difference is 1. P is 1, D is 2, difference is 1. D is 2, F is 3, difference is 1. So these transitions, that is S to P, P to D, that means it should go only to the next immediate level. Then only it is a allowed transition. Okay, D to F. Okay, all these are the transitions are allowed. Okay, so the in the Laporte you have to remember, if you consider parity, it should be always, you have to remember that the transition occurs between the unjarred to jarred is only allowed. Either G to U or U to G is only allowed, but not the same parity is forbidden. Okay, that is one thing. Then this is one thing. That is, it should be equivalent to plus or minus 1. And if I am talking in terms of symmetry, it should either be equivalent, the triple product should be either be equivalent to the totally symmetric irreducible representation, or it should contain the irreducible representations. These are the things you have to remember in the Laporte selection rules. Okay. After this, we will talk about the spin selection rule. So spin selection rule is here. So we know that the psi of an electron is the multiplication of the orbital and the spin. Okay. So we have done with this part. Okay. Now we will talk about only the how the electric dipole moment operators. Uh, that is the mu I is not having any impact on the mu s. Okay. So you can remove that, and when you see the equation 5, where I have written, yeah, this is a total equation. So this part we have done. Okay, what we said, this should be equivalent to the totally symmetric, or it should contain this totally symmetric irreducible representative. Now we will see this part. Okay, what is this part? That is the psi of the ground multiplied with the psi of the excited state of the spin of that particular electron. Okay, this direct product. Okay, whether it should be equivalent to 0 or whether it should not be equivalent to 0, that we have to see. So in this part, you have not written any electric dipole moment. That means this spin is not having any effect. Okay, so it is simply a spin, either clockwise or anti-clockwise. We are not talking about in x direction, y direction, or z direction. Okay, but if we talk about the orbitals, we know that the orbitals are oriented in the x, y, and z direction. So you have to take that mu in the x polarized, y polarized, or the z polarized. Okay. So how to know? So we will take these integrals of this. Okay. So this product, it should be equivalent to the delta ij. Okay. Now this I and j is nothing but the spin in the ground state. The spin is represented as I. When it is going to the excited state, it is represented as j. Okay, it is represented as j. So if the spin is equivalent, okay, what happens? This multiplication, okay, if this spin and this spin is equivalent, I will get 1. Okay. That is, the spin in the ground state and the spin in the excited state are equivalent. Okay. Then the product I am going to get is 1. If the spins are not equivalent, that is, if 1 is 0, okay, then this will become 0. Okay, that means the spins are not equivalent to j. Okay. I and j spins are not equivalent. Okay. So you just have to remember that if I'm getting a 0, same thing whatever we have written here, same thing we are showing in the form of the equation, that is, the spins in the ground and excited states are not equivalent, then the delta S will be not equal to 0, right? So if the spins are equal, the delta S value will be equal to 0. Delta S value will be equal to 0. So this combination will give you 0 if delta S is not equal to 0, and this product will not be equal to 0 when delta is equal to 0. Okay. So you have to remember that the spin selection rule can be stated as, if the transitions between wave functions of different spins are forbidden. Okay, that means if these two are not same, okay, it is a forbidden transition. Okay, and if it is a spin allowed transition, is electron is excited without change in its spin, so that is a allowed transition. So it should be like, the transition should be from singlet to singlet, doublet to doublet, triplet to triplet. Okay, and the transitions, that is singlet to triplet, doublet to quartet, you cannot have that. Okay, so one గుడ్డిగా ఒకటి గుర్తుపెట్టుకునేది ఏంటంటే, స్పిన్ సెలక్షన్ రూల్ లో whenever the electron is going from the, let me just write it here and show you. So whenever the so if I'm having a two excited levels, okay, Okay, this is the ground state. Okay, and this is the excited state. Fine. So I have an electron with the clockwise or anti-clockwise. Okay, suppose if this is a spin. Okay, that is in the clockwise it is going and it is plus half. Okay, so when it is excited to the next level, okay, it should be again be having the same spin. It should not change its spin. Okay, again it will be plus half only. That is, if it is rotating here clockwise, here also it will rotate clockwise only. Here also it is rotating clockwise, here also it is rotating clockwise. So it should not change the spin whenever it is going from the ground to the excited state. This is what you have to rectify. Okay, that means the ground state, that means singlet to singlet only, doublet to doublet only, triplet to triplet. Okay, and how do you know this? You know that spin multiplicity, this also we have spoken in the last class. Spin multiplicity 2s plus 1, you have to see. Okay, so if this spin multiplicity, if I'm having only one electron, the spin is half, so I will take 2 into half plus 1. So what will this be equal to? 2 and 2 cancel. Okay, so 1 plus 1, 2. So the 2s plus 1 value will become, if I'm having only one electron, and then the doublet. Okay, if it, then the transition should be again to one more thing, that is only doublet. So if I'm telling that it is doublet A1G, okay, to whatever the thing, it should be again a doublet T1G or whatever it is, T1U or whatever it is. Okay, so it should be always equivalent to the, this should be same. This is also doublet, this is also doublet. So these two are the allowed transitions. Okay, so I cannot have one here and two here. That is singlet to doublet. This is a forbidden transition. Okay, or 2 and 3, doublet to triplet. Again, that is a forbidden transition. So allowed is same thing. Spin multiplicity should be same. That means the electron should not change its spin. This is what you have to remember in the spin selection rule. Now we have studied about two rules, that is spin selection rule and the orbital selection rules. Okay. Now these rules will be applied, can be applied only when the molecule is a perfect structure without any deviations and all. Okay. But we know that all the transition methods you have D to D, DD transitions. Right? In all the transition methods, we are talking about the DD transitions. Now we are telling DD transitions are forbidden. Then how come the all the metal complexes are absorbing and we see that they are all colored, right? So how is that it is becoming an allowed transition? Because there is some relaxation. That is, the rules are not strictly adhered because the models are not idealized models. Okay, so you can tell that there is some relaxation, okay? And because of which you see that the DD transitions are becoming allowed. So there are three relaxations, okay, by which this DD can become equivalent. Okay, so how can you tell when there is some distortion? Okay, suppose if the perfect octahedron is going to a uh, tetragonal distortion. Okay, you have studied in the John Teller distortion, right? Tetragonal distortion. So what is that we have said? If it is going from a perfect octahedron to some other distortion, okay, then you can see that the DD transitions, instead of forbidden, it becomes colored. Okay. So whenever I am telling the octahedron is little bit distorted. Okay. So I am telling that in the octahedron, it is having center of symmetry. How do you represent a octahedron? We represent this way, right? So the metal here. Okay. So we have ligands here. 1, 2, 3, 4. Sorry. Okay, the diagram is dirty. Okay. So this is your octahedron. Okay, thinking that all the metal ligand bond lengths are same, assuming, okay, perfect octahedron. Now I am telling that if I travel, so this is my center of inversion, because if I travel from here to here and again same space, if I travel, I am getting the same ligand, L and L. Here also same thing, here also same thing. So this is having the center of inversion, that is I. So this is a centrosymmetric molecule. Suppose if this is little bit distorted, that is there is some elongation along the z axis. So what is happening? Or there is elongation, like one part is properly elongated. This part is like this. Then if I write ligands here, so what is happening? All the ML bonds are not same. So there is some distortion in the molecule. Okay. So what is happening? The I is lost here. Okay. It is not becoming exactly centrosymmetric. That means there is a loss here. Okay. So that is what we are telling. So if it is going from that to square planar or D4H, temporarily this will be removed. The center of inversion will be either permanently or temporarily it will be removed. So temporarily it will be for the tetragonal distortion, and permanently I can tell it is for the square planar. I am completely removing the Z. Okay. So this we are telling that it is due to the John Taylor effect. What is this? We have already studied, okay, in your first sem. This is due to the John Taylor effect, this distortion. If it is happening, what happens? The DD transitions which were forbidden in the beginning, now they are becoming the allowed transitions. So in the beginning, we said that this transition, that is T1G to A2G, is a forbidden transition. Okay, because why is that we are telling it is a forbidden transition? Just take the direct product of that. Okay, so if T1G is the ground state and A2G is the excited state. From this transition, that only I can know, right? T1G and A2G. Okay, and then when you see that direct product table, okay, you will get that the mu I value is, that is T1U. We know that X, Y, and Z is nothing but your T1U, right? So in between you put T1U. Okay, so this is nothing but when you do the direct product, you are getting all these terms, that is A2U. What is that you are supposed to get? You should supposed to get the A1G. Then only it will be allowed. That is totally symmetric. So this part is not having any of this one A1G. So this is a forbidden. That is what I told you in the Laporte. The direct product should be equivalent to the A1G, or at least it should have 1 as the A1G. Either is not having A1G at all. It should not containing. So this transition is a forbidden transition. Okay. Now we'll see when this T1G to A2G, how it becomes allowed when I'm going from the octahedral to the D4H, that is the square planar geometry. So how do you get D4H? Whenever we are elongating the octahedron along the z-axis, we are going to get this tetragonal distortion, that is the D4H. Okay, so you should know that the T1G in the octahedron, when you go to D4H, it will become A2G and EG. Okay, and the A2G, that is this excited state, it will become B1G in D4H. Okay, and T1U in octahedron, it will become EU plus A2U. So this is all from the uh, point group tables. You can know, okay, how this is getting converted. So just see how we are able to get this. Okay, so T1G into T1U into A2U. That is what we have to write, right? This is what I have to write. T1G into T1U into A2G. That is in the octahedron. So T1G is what? A2G plus AG in the D4H. Okay. Then T1U is what? EU plus A2G plus A2G and in D4H symmetry, the direct product becomes Eg into A2G into EU into B1G plus A2G plus Eg into A2U into B1G. So there is some ambiguity here. I'll cross check in the next class. Okay. So whatever it is, now this calculation is becoming A1. Okay. So when I'm going from tetrahedral to this, I'm getting the A1. So this is becoming partially relaxed. Even though it is not G, A1 is present. So instead of a forbidden, it is becoming a allowed transition. Okay, so one rule is whenever it is becoming distorted from from octahedral to the distorted complex, the forbidden transitions are a little bit relaxed and they are becoming allowed, partially allowed. Okay. Then the second one is whenever you can have this d and p orbitals mixing. Okay, so when you are talking about tetrahedral molecules, okay, the transition is from E to T2. Okay, and these are allowed as the direct product, that is E and T2 into T2 you are getting A1. So since this is having A1, this is a allowed transition, whereas mu I, if it is T2, where you don't write any G or U here because it is eccentric one, and from the tetrahedral character table, okay, these two are as E, and T2 will have the other one, that is the dxz, dyz and dxy. They are written as T2. Okay, so this will have a E and this is has T2. Now since these are xy and z direction, this will have both a mixing of D and P. Okay, so this T2 is partially U and partially G. Okay, and hence this DP mixing is there. Okay, because of which again the transition is allowed. So you can just take an example here. The octahedral complexes of tris ethylene diamine cobalt 3, okay, and so on. They have all these have this. Ethylene diamine will have nitrogen as the donor atoms, and if you take ACAC, that is acetyl acetonitrile, it will have oxygen atoms. Okay, so they have the symmetry D3. They don't have a perfect octahedral structure. So this A12 is allowed one, even though it is a DD transition. Okay, and E will have the combination of P and dxz, dyz, and also there is some P and D character mixing. So hence again this is a DP mixing is there. So you can tell that these DD transitions, that is, since it is having some of the U and G, so this is a forbidden. Even then it is, that selection rule is not applicable because you are telling there is some P and D mixing. So it is not a pure D to D transition. It is a D to P and D transition. So you can expect that it is a allowed transition. So one more thing is vibronic coupling. Okay, this I'll talk about in the next class. So only two things we have studied in the relaxation. One is change in the distortion. The second one is DP mixing. I'll talk about vibronic coupling in the next class. Okay. So with this, the selection rules will be done. Okay. So let's stop recording. Yeah.